Welcome to the Midnight Lyceum. Tonight is not about answers, or conclusions, or certainty. It is about slowing down enough to sit with the deepest questions we can ask. Questions about time, memory, probability, and what it means to be real in a universe that does not promise meaning by default. You don't need to follow every idea. You don't need to remember every detail. This is not a lecture. It is a journey. A quiet walk through the edges of modern cosmology, where physics becomes philosophy, and where thought itself begins to soften. So let your attention drift. Let your mind wander. Nothing here requires effort. Just listen and rest. The universe does not move with intention. It moves with likelihood. Over vast stretches of time, what happens most often is not what is dramatic, but what is probable. Close your eyes for a moment. Picture a room filled with air. Molecules bouncing, colliding, scattering in every direction. There is no hand guiding them, no blueprint, just motion and mathematics. Now imagine all those molecules, by pure chance, drifting into one corner of the room. All of them, every single one, leaving the rest in perfect vacuum. It could happen. It will happen. If you wait long enough. That is not a guess. It is not philosophy. It is the structure of probability itself. And it is where our story begins tonight. In the late 19th century, a physicist named Ludwig Boltzmann sat with a problem that would haunt him for the rest of his life. The problem was this. The second law of thermodynamics says that entropy, disorder, always increases. And yet here we are, in a world filled with stars, galaxies, life, structure. Where did all this order come from? Boltzmann's answer was elegant and unsettling. He said, perhaps the universe is not fundamentally ordered. Perhaps, most of the time, it is a featureless void, a cosmic equilibrium, nothing happening, nothing changing, just flatness. But every now and then, very rarely, there is a fluctuation, a random stirring, a momentary dip into something more organized. And maybe we live in one of those fluctuations. It is a beautiful idea, and it works, mathematically at least, but it comes with a cost. Let's talk about what entropy really is. We often think of it as chaos, disorder, messiness, but that is not quite right. Entropy is not a force. It does not push things toward disorder. It is simply a counting argument. Imagine a deck of cards. There are billions of ways to shuffle that deck, but only one way, one single arrangement, gives you the sequence ace through king in perfect order, all four suits aligned. If you shuffle randomly, you will almost never land on that arrangement. Not because the universe wants chaos, but because there are so many more ways to be disordered than ordered. That is entropy. That is the second law. It is not destiny. It is likelihood. And yet, the second law is not absolute, not rigid. Even a system near equilibrium, near that dull, flat, high entropy state, can fluctuate. For a moment, for a breath, molecules in a gas can drift together. A cup of lukewarm coffee can, for just an instant, get slightly warmer in one spot. It happens, but the larger the fluctuation, the greater the drop in entropy, the more rare it becomes. Not impossible, just improbable. A small fluctuation might happen once a minute. A larger one, once a century. A massive one, once in a trillion years. But if the universe lasts forever, even the rarest thing will happen eventually. And not just once. Again, and again, and again. This is where Boltzmann's cosmos begins to feel strange. Imagine a universe that has no beginning, no end, just equilibrium, stretching out in all directions, through all of time. Most of that time, nothing happens. But occasionally, vanishingly rarely, there is a dip, a bubble, a little island of order. Maybe that island is a galaxy. Maybe it is a planet. Maybe it is just a single molecule arranged in an interesting way. And then it fades, back into the nothing. Boltzmann realized something profound about this picture. If fluctuations are driven purely by probability, then small fluctuations vastly outnumber large ones. A universe with a single star is far more likely than a universe with a billion stars. A solar system is more likely than a galaxy. A planet, more likely than a solar system. And a single mind, one brain, flickering into existence with a set of false memories, convinced it is sitting on a planet under a sky full of stars, is more likely than an entire cosmos. That flicker, that lone disembodied brain, is what we now call a Boltzmann brain. And if Boltzmann's picture is correct, most observers in the history of the universe would not be like you and me. They would be these, random, alone, brief, false. Now, Boltzmann was not trying to scare anyone. He was trying to explain why we see order in a universe governed by entropy. His fluctuation model was an attempt at reconciliation, a way to say, maybe our cosmos is just a temporary bubble in an eternal sea of nothing. But even he recognized the problem. If small fluctuations are more common than large ones, then the typical observer in this model is not someone living on a real planet orbiting a real star. The typical observer is a ghost, a hallucination, a brain flickering into existence for a fraction of a second, with memories it never experienced and a world that does not exist. And if most observers are Boltzmann brains, then statistically speaking, you probably are one too. We will return to that thought. But first, let's sit with the structure underneath it. Because this is not really about brains. Not yet. This is about time, and probability, and the strange, patient mathematics of the inevitable. In an equilibrium universe, one that lasts forever, anything that can happen, eventually will happen. Not because the universe wants it to, but because probability does not care about meaning, only about counting. If there is even a 1 in a trillion chance that a certain pattern will emerge, then given enough time, it emerges. And not just once. Again, and again, and again, forever. This is what modern physicists sometimes call the Poincare recurrence theorem. The idea that a system, left alone long enough, will eventually return to any state it has ever been in. Your room, this moment, this breath. In an eternal universe, it will all happen again, and again, and again, not because it is fated, but because it is possible. And in infinity, possibility becomes inevitability. So let's return to Boltzmann's universe. A vast, eternal equilibrium, mostly nothing, but punctuated, every trillion years, every quadrillion years, by tiny islands of order. Most of those islands are small. A star, a planet, a molecule. Some are larger, a galaxy, a cluster, and very rarely, an entire universe like ours. A cosmos filled with structure, billions of galaxies, trillions of stars. But here is the key. If you are trying to explain why an observer exists, why there is someone here to notice the order, you do not need the whole universe. You only need a brain. A brain is far simpler than a galaxy. It requires far less order, far less of a dip in entropy. And so, in Boltzmann's cosmos, brains that fluctuate into existence alone, disembodied, brief, filled with false memories of a world that never was, vastly outnumber real observers in real worlds, by an incomprehensible margin. This is the heart of the Boltzmann brain paradox. If our cosmology predicts that most observers are hallucinations, then we have a problem, because either we are extraordinarily lucky, or the cosmology is wrong. Tonight, we are going to walk through that paradox. Slowly, carefully, we are going to ask, what does it mean to be an observer? What does it mean to be real? And we are going to explore the possibility, the uncomfortable, haunting possibility, that the structure of probability itself may have woven something false. Not intentionally, but inevitably, because in a universe governed by likelihood, the most common thing is not always the most meaningful, and the rarest thing may be truth itself. Let's begin. And once we include observers in that accounting, once we admit that awareness itself is a physical pattern, the story quietly changes. A Boltzmann brain is not a monster. It is a consequence, a strange arithmetic result that appears when time becomes very large. Let's be clear about what we are talking about. A Boltzmann brain is not something anyone has ever seen. It is not something that has been detected, measured, or observed in any laboratory. It is a thought experiment, a hypothetical, a mathematical ghost conjured from the equations of thermodynamics and probability. but it is a ghost worth meeting, because what it reveals is not a flaw in reality, but a flaw in certain ways of thinking about reality. So what, exactly, is a Boltzmann brain? In the simplest terms, it is a self-aware mind that appears spontaneously from random fluctuations. Not grown, not evolved, not built, just assembled, by chance, out of the background noise of a universe at equilibrium. Imagine the cosmos at its end. All the stars have burned out. All the galaxies have drifted apart. All the black holes have evaporated. What remains is a thin, featureless soup of particles. Photons, neutrinos, the faintest whisper of radiation. Nothing is happening. Nothing will ever happen again. Or so it seems. But remember, in equilibrium, fluctuations still occur. Rare ones, tiny ones, moments when, by pure accident, particles align in some temporary pattern before scattering again. Most of these fluctuations are meaningless. A few atoms briefly cluster. A photon bounces at an unusual angle. Nothing worth noticing. But every now and then, very, very rarely, a larger fluctuation occurs. And if you wait long enough, trillions upon trillions of years, one of those fluctuations might, by pure chance, assemble something complex. Something like a brain. Not a skull. Not a body. Just the brain itself. Floating in the void. Functional. Conscious. Aware. For a single moment. And then it dissolves. That is a Boltzmann brain. Now, here is where it gets strange. This brain does not appear as a blank slate. It does not wake up confused, wondering where it is. Because the fluctuation that created it also, by chance, arranged its neurons in a very specific pattern. A pattern that encodes memories. Memories of a life it never lived. Memories of a childhood. A family. A home. A sky. A world. All of it false. All of it convincing. The brain believes it is you. Or me. Or anyone. It believes it is sitting in a room. Or walking down a street. Or lying in bed listening to a voice in the dark. And then, a moment later, it is gone. The fluctuation ends. The particles scatter. The brain dissolves back into the equilibrium. And the universe continues. Silent. Empty. Waiting for the next impossible accident. This is not science fiction. This is thermodynamics. If the universe lasts forever, and if it eventually reaches equilibrium, then this will happen. Not once. Not twice. But infinitely many times. Because in an eternal equilibrium, anything that can happen will happen. And a brain is just a configuration of particles. Rare, yes. Extraordinarily rare. But not impossible. And in infinity, the rare becomes routine. So why do physicists care about this? Why spend time thinking about disembodied brains flickering in and out of existence trillions of years from now? Because the Boltzmann brain is not really about brains. It is about observers. And in cosmology, observers are not just passive witnesses. They are part of the equation. Let me explain. When we talk about the universe, we are not just talking about stars and galaxies and space-time. We are also talking about the beings who observe it. Us. Consciousness. Awareness. And one of the deep questions in cosmology is this. What kind of universe would produce observers like us? Or to put it another way, if you pick a random observer from all the observers that exist across all of time, what kind of observer should you expect to be? This is called the typicality problem. And here is where the Boltzmann brain becomes more than a curiosity. Because if we live in a universe that eventually reaches equilibrium and stays there forever, then the vast, overwhelming majority of observers that will ever exist are not people like us. They are Boltzmann brains. Think about it. Our universe, right now, is filled with stars, planets, life, structure. Billions of years of cosmic history have produced trillions upon trillions of potential observers. But equilibrium lasts forever. And in that endless stretch of time, the number of Boltzmann brains that fluctuate into existence, however rare each individual one might be, will eventually dwarf the number of normal observers by an incomprehensible margin. If you were to count every human who has ever lived, every alien on every planet, in every galaxy, every conscious being produced by the entire history of cosmic evolution, and then compare that number to the number of Boltzmann brains that will appear over the infinite future, it is not even close. The Boltzmann brains win, by infinity to one. And so, if you are a typical observer in this cosmology, you you should expect to be a Boltzmann brain. Not a real person. Not someone with a real past. Just a fluctuation. A brief, convincing hallucination. Do you see the problem? This is not a question about what is true. It is a question about what the theory predicts. And if a cosmological theory predicts that most observers are hallucinations, then that theory is telling us something uncomfortable. Either we are extraordinarily, impossibly lucky, real observers in a universe dominated by fake ones, or the theory itself is wrong. Most physicists choose the second option. They treat the Boltzmann brain problem as a diagnostic, a warning sign, a way of testing whether a cosmological model makes sense. If your model predicts that the universe will be dominated by Boltzmann brains, then your model is probably flawed. Not because Boltzmann brains are impossible, but because they should not be typical. We should not have to invoke extraordinary luck to explain why we are real. So what kind of cosmology leads to this problem? The key ingredient is equilibrium. Specifically, a long-lived equilibrium. A universe that reaches a stable, featureless state and stays there for an extraordinarily long time. Or forever. This is sometimes called heat death. The idea is old. It goes back to the 19th century, when physicists first started worrying about the second law of thermodynamics. If entropy always increases, they wondered, then eventually the universe will reach maximum entropy. Everything will be spread out, uniform, cold, dead, no stars, no structure, no change, just equilibrium. And once the universe reaches that state, it stays there. Forever. At least, that is one possibility. And in that possibility, the Boltzmann brain problem becomes sharp. Because equilibrium is exactly the kind of environment where fluctuations matter. Where rare, random events, however unlikely, have infinite time to occur. And where the cheapest way to produce an observer is not through billions of years of stellar evolution and planetary formation and biological complexity, but through a single, spontaneous fluctuation. One brain, one moment, one lie. It is far more probable than an entire universe. And so, in equilibrium, it happens far more often. Not because the universe wants to deceive. Not because there is some conspiracy or malicious intent. But simply because of the mathematics. Because probability does not care about meaning. It only cares about counting. And when you count the ways to make an observer, a Boltzmann brain is cheaper. Now, here is the thing. We do not live in equilibrium. Not yet. Our universe is young, dynamic, filled with gradients and structure and change. Entropy is increasing, yes, but we are nowhere near maximum entropy. We are still in the early chapters. And that is why we are not Boltzmann brains. We are the product of a real history, a real Big Bang. Real stars, real planets, real evolution. We are expensive observers. But if our universe does eventually reach equilibrium, and many models suggest it will, then the Boltzmann brain problem is waiting for us in the far future. Not as a threat, but as a puzzle. A puzzle about what it means to be typical, what it means to be real, and what kinds of cosmologies make sense. Because if a theory predicts that the future is dominated by fake observers, then maybe that theory is missing something. Maybe the universe does not last forever in equilibrium. Maybe equilibrium is unstable. Maybe there are mechanisms we do not yet understand that prevent the kind of long-lived, featureless future where Boltzmann brains thrive. Or maybe the way we think about observers is wrong. Maybe typicality is not as simple as counting. Maybe there is something about the structure of consciousness, or memory, or causation that privileges real observers over fluctuation-born ones. These are open questions, and they matter because the Boltzmann brain is not just a curiosity. It is a lens, a way of asking, does our cosmology make sense? Does it predict a universe where beings like us are natural, or extraordinarily unlikely? And if the answer is unlikely, then we need a better cosmology. So as we move forward, keep this in mind. The Boltzmann brain is not the enemy. It is the alarm, a signal that something, somewhere in our understanding, might be off. And in the sections to come, we are going to explore what that something might be. We are going to ask, what if the universe we see is not the universe that is? What if structure itself is a fluctuation? What if memory is unreliable? What if the past we believe in never actually happened? These are not comfortable questions, but they are the questions the Boltzmann brain forces us to ask. And tonight, we are going to sit with them. slowly, carefully, without fear, because the truth, whatever it is worth finding, even if it flickers. To understand why such strange consequences arise, we have to talk about the quiet warmth of empty space itself. Even emptiness is not truly cold. Even silence carries a faint temperature. This is one of the most beautiful and unsettling discoveries of modern physics, and it changes everything about how we think about the far future. Let's start with what we know. Our universe is expanding, not just growing, but accelerating. Galaxies are moving away from each other faster and faster, driven by something we do not fully understand. We call it dark energy. It is not matter. It is not radiation. It is something else, something woven into the fabric of space itself. A kind of pressure, a push. And the best model we have for dark energy is something called the cosmological constant. The cosmological constant is simple, in a way. It says that empty space has energy. Not much, just a tiny amount, but it is always there, everywhere, uniform, unchanging. And because space itself has energy, and because the universe is expanding, that energy does not dilute. It does not spread out. It stays constant, which means that as the universe grows, the total amount of dark energy grows with it. And that energy drives the expansion faster, and faster, and faster. This is the future we are heading toward. A future where the expansion of the universe does not slow down, does not stop, but accelerates forever. A future where galaxies drift apart until they disappear beyond the horizon of what we can see. A future where space itself becomes emptier and emptier, until nothing remains but the faint, uniform hum of the cosmological constant. This kind of universe has a name. It is called de Sitter space, named after the Dutch astronomer Willem de Sitter, who first studied its properties over a century ago. And de Sitter space has a strange feature. It has a horizon, not like the horizon of the Earth, where the curve of the planet blocks your view. This is a causal horizon, a boundary in space-time, a line beyond which you can never see, never reach, never influence. Because space is expanding so fast that light from beyond that horizon can never catch up to you. You are isolated, trapped, not by walls, but by geometry. And here is where things get strange. Horizons in relativity are not just boundaries. They are thermodynamic objects. They have temperature. This was first discovered by Stephen Hawking in the 1970s, in the context of black holes. He showed that the horizon of a black hole radiates, gently, slowly, as if it were warm, not because there is fire at the horizon, but because the horizon itself, the boundary between what can escape and what cannot, creates a kind of thermal glow. A few years later, physicists Gary Gibbons and Stephen Hawking extended this idea to de Sitter space. They showed that the cosmological horizon, the boundary of what you can see in an accelerating universe, also has a temperature, a tiny temperature, almost nothing, far colder than the coldest place in the universe today, but not zero. And that changes everything, because if space has a horizon, and that horizon has a temperature, then space itself acts like a thermal bath. A bath so cold, so thin, so faint, that it is almost nothing. But almost is not the same as exactly. And in an infinite future, almost nothing is enough. Let me explain. In thermodynamics, temperature is tied to fluctuation. The warmer something is, the more its particles jiggle. The more they move randomly. The more they occasionally, by chance, arrange themselves into temporary patterns. Even at very low temperatures, this still happens. Just more slowly, more rarely, but it still happens. And in de Sitter space, where the horizon has a temperature, where the universe expands forever, where time stretches on without end, those rare fluctuations have infinite time to occur. This is the setup for the Boltzmann Brain problem in a cosmological constant universe. Because if space acts like a thermal bath, even a very cold one, then eventually, over unimaginable stretches of time, random fluctuations will occur. Most will be tiny, a few particles clustering, a photon scattering in an unusual way. But some will be larger, and some, vanishingly rarely, will be large enough to form something complex. Something like a brain. Not built, not evolved, just fluctuated. And because the universe stays in this de Sitter phase forever, or at least for an absurdly long time, the number of such fluctuations, however rare, eventually becomes enormous. larger than the number of real observers produced by stars and planets and biology, by an incomprehensible margin. This is the scenario that physicists like Leonard Susskind, Matthew Kleban, and others have studied. And what they found is troubling. In a universe with a positive cosmological constant, one that expands forever, with a horizon that has a temperature, the Boltzmann Brain problem does not go away. It gets worse, because ordinary astrophysical life has a limit. Stars burn out, planets cool, galaxies drift apart. Eventually, there is nowhere left for biology to exist. But the horizon temperature never goes away. It persists, forever. And so, long after the last star has died, long after the last planet has frozen, long after every trace of real observers has vanished, the fluctuations continue. Rare, slow, patient, but infinite. And in that infinite future, the Boltzmann brains dominate. Not because they are more common in any given moment, but because there are so many more moments. Infinity overwhelms everything. Now, this is not a proof that Boltzmann brains exist. It is not a claim that we are living in de Sitter space right now, or that the cosmological constant will last forever. It is a warning, a signal that something in this picture might be wrong. Because if your cosmological model predicts that the far future is dominated by fake observers, beings with false memories, flickering in and out of existence in an empty void, then that model is probably incomplete. Either the universe does not stay in a de Sitter phase forever, or there is something about the way we count observers that is missing a key ingredient. Or there is something about horizons, or temperature, or quantum mechanics that we do not yet fully understand. These are open questions, deep ones, and they matter because they shape how we think about the ultimate fate of the universe. Will expansion continue forever? Will the cosmological constant remain constant? Will the horizon temperature persist, or will it somehow decay? We do not know. But the Boltzmann brain problem gives us a way to test our ideas. If a cosmological model leads to a Boltzmann brain-dominated future, that is a red flag, a reason to look more carefully, a reason to ask, is this really what the universe does? Or is this just what our current models predict, because they are missing something? So let's sit with this for a moment. Imagine the far future, trillions of years from now, quadrillions, googles, numbers so large they have no name. All the stars are gone. All the galaxies have drifted beyond the horizon. Space is dark, empty, silent, but not quite. There is still the faint warmth of the horizon. The gibbons, Hawking temperature. Almost nothing, but not nothing. And in that almost nothing, particles occasionally fluctuate. Most of the time, these fluctuations are meaningless. A brief clustering, a random ripple, nothing worth noticing. But every now and then, so rarely that the wait between events is longer than the entire history of our universe so far, something larger happens. A more complex pattern, a more ordered arrangement. And if you wait long enough, one of those patterns will be a brain. Conscious, aware, convinced it is real, for one moment, and then gone. And this will happen again, and again, and again, forever. Or at least, until something changes. Until the cosmological constant decays. Until the horizon disappears. Until the assumptions we have made about the far future turn out to be wrong. But if nothing changes, if the universe really does expand forever with a positive cosmological constant, then this is what the mathematics predicts. Not as a certainty, but as a consequence. A strange, patient arithmetic of infinity. And that is why physicists take the Boltzmann brain problem seriously. Not because they believe we are Boltzmann brains, but because the fact that the math allows for it means something is incomplete. There is a piece of the puzzle we are missing, a way out of the paradox, and finding that way out might teach us something profound about the nature of the cosmos, about time, about observers, about what it means to be real. So as we move forward, remember this. The horizon has a temperature, and that temperature, however faint, is enough. Enough to sustain fluctuations, enough to allow for rare, impossible things. Enough to create the conditions where a Boltzmann brain could, in principle, appear. Not today, not tomorrow, but in the vast, patient future. And the question we are left with is this. How do we reconcile that possibility with the fact that we are here, now apparently real, apparently the product of a long and genuine history? How do we make sense of a cosmology that predicts we should be fake? That is the puzzle. And in the next section, we will begin to explore it. Slowly, carefully, without rushing, because the answer, whatever it is hidden somewhere in the mathematics of memory, causation, and time. And we are going to find it, together. And now, we slow time down even further. When time stretches far enough, rarity stops being rare. We need to talk about time. Not the time you experience. Not the hours or days or years that mark your life. But time on a scale so vast that it stops feeling like time at all. It becomes something else. Something patient. Something that erases meaning through sheer duration. Let's start with a number. The universe, as we understand it, is approximately 13.8 billion years old. That is the time since the Big Bang. The time during which stars have formed, galaxies have clustered, planets have cooled, and life has emerged. 13.8 billion years. It feels like a long time. And it is. By human standards, it is incomprehensible. But in the context of Boltzmann brains, it is nothing. Not even a blink. Because the timescales on which Boltzmann brains are expected to appear, if they appear at all, are not measured in billions of years. They are measured in numbers so large that we do not have intuitive names for them. Numbers that make the age of the universe look like a single heartbeat in an endless life. Let me try to give you a sense of scale. Imagine waiting 1 billion years, 1,000 million years, long enough for entire galaxies to change shape, long enough for stars to be born, live, and die. Now multiply that by a billion. You are now at a billion years. A number written as 1 followed by 18 zeros. That is starting to feel large, unimaginable, even. But we are not even close yet. Multiply by a billion again, and again, and again. Keep going, keep multiplying, until the number of zeros in your number is itself a number too large to write down. And then keep going. This is the kind of timescale we are talking about. Not millions of years, not billions, not trillions, but numbers so enormous that they exist only in the abstract. Numbers that have no referent in physical reality as we know it. And yet, in a universe that expands forever, in a de Sitter space with a horizon temperature, these timescales are real. They are waiting, because probability does not care how long something takes. It only cares whether it can happen. And if it can happen, and if time is infinite, then eventually it will happen. Not once, infinitely many times. Now, there are different ways to estimate when a Boltzmann brain might appear. Some estimates come from quantum mechanics. The idea that, at the quantum level, particles can tunnel through energy barriers. That configurations can spontaneously shift from one state to another, however unlikely. Other estimates come from classical thermodynamics. The idea that, in a thermal bath, fluctuations occur randomly, and that given enough time, a large enough fluctuation will assemble something complex. The details differ, the mechanisms differ, but the conclusion is the same. Boltzmann brains, if they exist at all, appear on timescales that are fantastically, unimaginably, absurdly long. Far longer than the current age of the universe. Far longer than the time it will take for the last stars to burn out. Far longer than the time it will take for black holes to evaporate. So long that, for all practical purposes, they might as well be impossible. Except, they are not impossible, just improbable. And improbable, given infinite time, becomes inevitable. This is where the Boltzmann brain problem becomes entangled with something called the measure problem in cosmology. The measure problem is a deep and technical issue, but the core idea is simple. How do you count observers in a universe that might be infinite? Or in a multiverse where different regions have different properties? Or in a timeline that stretches forever? If there are infinitely many observers, then ratios stop making sense. Fractions become meaningless. The concept of typical breaks down. And yet, we still want to ask, what kind of observer should you expect to be? In a universe with a finite number of observers, this is straightforward. You count them. You see which kind is most common. Done. But in an infinite universe, or in an eternally expanding one, the counting never stops. And depending on how you do the counting, what you consider early versus late, what regions you include, what cutoffs you impose, you can get wildly different answers. This is the measure problem, and the Boltzmann brain is one of its most troubling manifestations. Because if you count observers over all of time, and if the universe expands forever with a horizon temperature, then the number of Boltzmann brains is infinite. And the number of real, evolved observers, however large, is finite. Infinity beats any finite number. And so, by that counting, the typical observer is a Boltzmann brain. But this is not a problem for the near future. It is not something that affects us now, or in 1,000,000 years, or in 1,000,000,000,000 years. It is an end-of-time thought experiment. A question about what happens when you follow a cosmological theory to its ultimate conclusion. When you take the equations seriously and ask, what do they predict in the limit of enormous time? And the answer, in many cases, is uncomfortable. Because in a Boltzmann brain-dominated picture, the story of the universe flips. The part we think of as important, the stars, the galaxies, the planets, the biology, becomes a brief prologue. A short transient phase. A flash. And the main act, the part that lasts forever, is randomness. Fluctuations. Rare, meaningless, isolated moments of order in an endless sea of equilibrium. That is the cosmology. And it feels wrong. Not because we know it is wrong, but because it makes us real, evolved observers, extraordinarily atypical. It makes our existence an accident so unlikely that it barely registers in the grand counting. And that challenges something fundamental. It challenges the way we use evidence to confirm theories. Normally, the process goes like this. We observe something. We build a theory to explain it. We test the theory. If the theory predicts what we observe, we gain confidence in it. But what if the theory predicts that most observers are delusional? What if it says that the vast majority of beings who think they are observing a real universe are actually Boltzmann brains with false memories? Then the chain breaks down. Because if you are probably a Boltzmann brain, then your observations are probably not reliable. Your memories of the past are probably false. Your perception of order is probably a coincidence. Your scientific theories are probably built on hallucinations. And so the theory undermines itself. It predicts that the evidence supporting it is not real. This is why the Boltzmann brain problem is not just a cosmological puzzle. It is an epistemic one, a problem about knowledge, about certainty, about what it means to trust your observations. And that is why physicists take it seriously. Not because they believe Boltzmann brains exist, but because the fact that a theory predicts them means something has gone wrong. Either the theory is missing something, or our assumptions about time, or infinity, or typicality are flawed, or the way we count observers needs to be reconsidered. These are not small questions. They touch the foundations of cosmology, of how we understand the universe's past, present, and future. And the Boltzmann brain, strange as it is the tool that brings these questions into focus. So let's sit with this for a moment. Imagine the universe, trillions upon trillions of years from now. All the stars are gone. All the galaxies have drifted beyond the horizon. The cosmos is dark, cold, empty. But not quite. There is still the faint hum of the horizon temperature, the quiet warmth of empty space itself. And in that warmth, fluctuations occur. Slowly, rarely, patiently. Most are meaningless. A few particles cluster. A photon scatters. Nothing worth noticing. But every now and then, so rarely that the wait is longer than the entire age of the universe so far, something larger happens. A brain, conscious, aware, convinced it is real, for one moment, and then it is gone. And this continues, forever, again and again and again. While the real observers, the ones like us, the ones produced by stars and planets and evolution, are long gone. Our era, however long it lasted, is over. Finished. A closed chapter. And the universe continues. Patient, unchanging, waiting for the next fluctuation. That is the picture. And the question we are left with is this. If that is what the equations predict, then what are we? Are we the rare, early observers? The lucky ones who exist in the brief prologue before the infinite randomness begins? Or are we already part of the randomness? Already Boltzmann brains, convinced of a history that never was? The math does not tell us. It only tells us that one of those options is overwhelmingly more probable than the other. And that is the problem. Because we want to believe we are real. We want to trust our memories. We want to think that the stars we see, the ground we stand on, the history we remember, is genuine. But if the theory says we are probably not, then what do we do with that? Do we reject the theory? Or do we accept that knowledge itself might be less certain than we thought? This is not a question with an easy answer. But it is a question worth asking, because the Boltzmann brain is not just a curiosity. It is a mirror, a way of testing whether our cosmological models make sense, whether they predict a universe where observers like us are natural or impossibly rare. And if the answer is rare, then we need to rethink something. Not because the universe owes us an easy answer, but because a theory that predicts we are probably hallucinating is not a theory we can use. It collapses under its own weight. And so the Boltzmann brain, strange and abstract as it is, becomes scientifically important. Not because it is real, but because it shows us where our understanding breaks down, where the mathematics leads to conclusions we cannot accept, and where perhaps a new idea is needed. An idea that preserves the structure of cosmology without drowning us in an infinite sea of false observers. We are looking for that idea, and in the sections to come, we will explore what it might be. Slowly, carefully, without rushing, because the answer, whatever it is worth finding, even if it takes a very, very long time. And when time grows without bound, we are forced to ask how we count anything at all. Infinity does not behave like large numbers. It breaks intuition quietly. We need to talk about a problem that sits at the heart of modern cosmology. A problem that sounds abstract, even mathematical, but that changes everything about how we think about the universe. It is called the measure problem, and it arises whenever we try to count things in a universe that might be infinite. Let me start with something simple. Imagine you have 10 marbles. 5 are red, 5 are blue. If you pick one at random, what is the probability that it is red? Easy, 50%. Now imagine you have 100 marbles. 60 red, 40 blue. Pick one at random. What is the probability? 60%. This works because the total is finite. You can count the marbles. You can form ratios. You can calculate probabilities. But what if you have infinitely many marbles? Infinitely many red. Infinitely many blue. Now what is the probability that you pick red? The question stops making sense. Because infinity divided by infinity is not a number. It is undefined. It could be anything. 50%, 90%, 1%. It depends entirely on how you count. Do you count all the marbles at once? Do you count them in groups? Do you count them in a particular order, or in a particular region of space? Each method gives a different answer, and none of them is obviously correct. This is the measure problem, and it shows up in cosmology whenever we try to ask, what is the typical state of the universe? What is the typical kind of observer? Because if the universe is infinite, or if certain models of cosmology, like eternal inflation, predict effectively infinite space-time volume, then counting becomes ambiguous. You cannot just count observers and form ratios. You have to decide how to count, what regions to include, what times to consider, what weighting scheme to use, and depending on those choices, you get wildly different answers. In some counting schemes, evolved observers like us are typical. In others, Boltzmann brains dominate. In still others, even stranger things appear. And there is no universal rule that tells you which counting scheme is right. This is not a bug. It is a feature of infinity. Infinity does not behave like large numbers. It has its own logic, its own strange arithmetic. And when you try to apply the usual tools of probability and statistics to infinite settings, those tools break down. So cosmologists have developed something called a measure. A measure is a formal way of assigning weights to different regions, times, or events in an infinite universe. It is a rule for counting, a way of turning the infinite into something manageable. But here is the problem. Different measures give different answers, and there is no consensus on which measure is correct. Some measures are based on volume. You weight regions by how much space they contain. Others are based on time. You weight observers by when they appear in cosmic history. Still others are based on causal structure. You weight observers by what they can see, what they can influence, what horizons surround them. Each of these measures is mathematically consistent. Each follows a clear set of rules, but they do not agree. In some measures, Boltzmann brains are rare. In others, they dominate completely. And so the question of whether we should expect to be Boltzmann brains depends, in part, on which measure you choose. This is troubling, because science is supposed to give definite answers, not answers that depend on arbitrary choices about how you do the counting. And yet, in an infinite universe, or in a cosmology with eternal inflation, those choices seem unavoidable. Eternal inflation is a scenario where the universe does not just expand, but keeps inflating forever in some regions. New pockets of space continually form. Some of those pockets stop inflating and settle into more familiar states, like our observable universe. But others keep going, eternally. In this picture, space-time becomes vast, effectively infinite, and that means there are infinitely many regions, infinitely many observers, infinitely many histories, and when you try to ask, what is typical? You run into the measure problem immediately, because typical compared to what? Counted how? If you count by volume, certain kinds of regions dominate. If you count by number of observers, different regions dominate. If you count by proper time, how much time elapses along different world lines, you get yet another answer. And in some of these counting schemes, pathologies emerge. Strange predictions, absurd conclusions, observers that do not make sense as typical, even though the math says they should be. One famous example is something called Boltzmann babies. This is a term coined by physicists Raphael Busso, Ben Free-Vogel, and Aisheng Yang, in a paper analyzing a particular measure in eternal inflation called the proper time measure. They found that, in this measure, the typical observer is not a fully formed adult human, not even a Boltzmann brain, but something in between, a young observer, a child, a baby, born not through biology, but through fluctuation, existing for a moment, and then gone. This prediction is absurd, not because it violates the laws of physics, it does not, but because it does not match what we observe. We are not Boltzmann babies. We have long histories, complex lives, consistent experiences, and yet the measure predicts we should be something else. This is a measure pathology, a sign that the measure itself is flawed, that the way we are doing the counting does not match reality. And the Boltzmann brain problem is another example of the same kind of pathology, a prediction that, if taken seriously, would imply we are not what we think we are. So what do? We adjust the measure. We look for better ways of counting, ways that predict we are typical in a sensible way. But here is the challenge. There is no universal principle that tells us which measure is correct. We have to choose, and that choice is guided, in part, by what we want the answer to be. We want the measure to predict that evolved observers like us are typical, that our memories are real, that our experience of a long, lawful cosmic history is genuine. And if a measure predicts otherwise, if it says we should be Boltzmann brains, or Boltzmann babies, or some other strange fluctuation, we reject it. Not because we can prove it is wrong, but because it does not match what we observe. This is not circular reasoning exactly. It is a kind of self-consistency check. We are trying to find a measure that makes sense of the fact that we exist, here, now, with the experiences we have. And if a measure predicts that beings like us are vanishingly rare, then that measure is probably not the right one. Or, at the very least, it suggests that something deeper is missing from the theory. One avenue of exploration comes from physicist André Linder, who has worked extensively on eternal inflation and the measure problem. Linder points out that not all vacuum states, the different possible configurations of spacetime and fields, are equally stable. Some vacua last forever, others decay. They tunnel into lower energy states, or collapse, or transition into something else. And that decay can change the counting, because if a vacuum state decays, then it does not contribute to the infinite future. It does not linger forever, producing observers through rare fluctuations. It ends, and that ending can prevent Boltzmann brains from dominating. Linder calls these decaying states sinks, places where cosmic evolution comes to a halt, or transitions into something different. And in a landscape of many possible vacua, some stable, some unstable, the presence of sinks can dramatically change what kinds of observers are typical. If the late-time vacuum states, the ones the universe settles into after stars burn out and galaxies drift apart, are not perfectly stable, if they decay on some timescale, however long, then the infinite future is cut off, or at least changed, and Boltzmann brains, which rely on infinite time to become numerous, might not dominate after all. This is not a complete solution. It is more of a direction, a way of thinking about the problem, but it highlights something important. The longevity of vacuum states matters. If the far future is truly eternal, truly stable, truly at equilibrium, then Boltzmann brains are hard to avoid. But if something changes, if the vacuum decays, if there is some mechanism that prevents the universe from lingering forever in a de Sitter-like state, then the counting changes, and evolved observers might remain typical. This is why the Boltzmann Brain problem is tied to questions about the ultimate fate of the universe, about whether the cosmological constant is truly constant, about whether space-time itself is stable in the far future. We do not know the answers yet, but the Boltzmann Brain gives us a way to test our ideas. If a cosmological model, combined with a particular measure, predicts that Boltzmann brains dominate, that is a red flag, a sign that something is wrong, either with the model, or with the measure, or with our understanding of what counts as typical. And so, in modern cosmology, the Boltzmann brain has become a filter test, a way of checking whether a framework is viable. If it passes the test, if it predicts that evolved observers like us are typical, then it is worth exploring further. If it fails, if it drowns us in an infinite sea of fluctuation-born hallucinations, then something needs to change. This is not about fear. It is not about avoiding an uncomfortable conclusion. It is about building theories that are internally consistent. Theories that predict a universe where knowledge is possible, where observation is reliable, where the past we remember is real. Because if the theory says the past is probably false, then the theory undermines itself. And that is where we turn next, to the idea of cognitive instability. The notion that a theory can be mathematically sound, logically coherent, and still collapse under its own weight. Because it predicts that the very process by which you arrived at it is unreliable, that your memories are false, that your observations are accidents, that your reasoning is a fluctuation. And if that is what the theory says, then you cannot believe it. Not because it is wrong, but because believing it requires trusting evidence that the theory itself says is probably fake. This is the loop, the paradox, the place where cosmology turns inward and questions itself. And it is where we are headed now. Slowly, carefully, without fear. Because the answer, whatever it is, lies not in avoiding the question, but in facing it directly, and asking, what does it mean to know anything at all? This is where the paradox turns inward. A theory that erases trust, erases itself. We have been talking about the Boltzmann brain as a cosmological problem, a puzzle about observers, entropy, and time. But now we need to turn the lens around and look at what the Boltzmann brain does to the act of thinking itself. Because this is not just about physics. It is about belief, about certainty, about whether you can trust the thoughts you are having right now. And that is where things become deeply, quietly unsettling. Let me explain. Imagine you are a scientist. You have studied cosmology for years. You understand thermodynamics, general relativity, quantum mechanics. You have looked at the data, examined the equations, and arrived at a conclusion. The universe will expand forever, eventually reaching a de Sitter-like state, and in the infinite future, Boltzmann brains will vastly outnumber evolved observers. You are confident in this theory. The math checks out. The evidence supports it. Everything fits. And then you realize something. If this theory is correct, then you're almost certainly a Boltzmann brain. Not because you want to be, not because there is any direct evidence for it, but simply because, in this cosmology, Boltzmann brains are overwhelmingly more common than real observers. And if you are a typical observer, then statistically, you should expect to be one of them. So you accept it. You say, yes, I am probably a Boltzmann brain. But then a second thought follows. If you are a Boltzmann brain, then your memories are false. Your education never happened. The data you examined does not exist. The equations you trust were never derived by anyone. They are just patterns in your neurons, assembled by random chance, convincing you of a history that never was. Which means, the theory you just accepted is not justified. Because the evidence you used to justify it is probably fake. And so the theory undermines itself. This is what philosopher and physicist Sean Carroll calls cognitive instability. It is the idea that a theory can be mathematically coherent, logically consistent, and still be unusable. Because if believing the theory gives you reasons to distrust the evidence that supports it, then the theory collapses under its own weight. It is not that the theory is wrong, exactly. It is that it cannot be justifiably believed. Because belief requires trust. Trust in your senses. Trust in your memory. Trust in the chain of reasoning that led you to the conclusion. And if the conclusion itself says that chain is probably a hallucination, then what are you left with? Nothing. A void. A theory that, if true, erases the ground it stands on. This is not a small problem. This is not a technicality. This is a fundamental breakdown in the logic of scientific confirmation. Normally, science works like this. You observe something. You form a hypothesis. You test it. If the hypothesis predicts what you observe, your confidence in it increases. If it fails, you revise it. This process depends on the assumption that your observations are real, that your memory of past experiments is reliable, that the evidence you are using to evaluate the theory is genuine. But in a Boltzmann brain-dominated cosmology, that assumption breaks down. Because if most observers are Boltzmann brains, then most observations are false. Most memories are fabricated. Most chains of reasoning are built on nothing. And so the usual process, evidence supports theory, theory gains credibility, stops working. The theory predicts that the evidence is unreliable. And if the evidence is unreliable, the theory is not supported. And if the theory is not supported, why believe it? You end up in a loop. A strange, self-defeating loop. If you are confident you are a Boltzmann brain, you also become confident that your reasons for believing that are delusional. And if your reasons are delusional, you should not be confident. But if you are not confident, then maybe you are not a Boltzmann brain after all. But if you are not, then the theory says you probably are. And around it goes. This is cognitive instability. And it is why cosmologists treat Boltzmann brain-dominated theories not as interesting predictions, but as warning signs. Red flags. Signals that something has gone wrong. Because a theory that undermines its own justification is not a theory you can use. It is not a theory you can live with. It is not a theory that explains anything. It is a dead end. And so, when a cosmological model predicts that Boltzmann brains dominate, physicists do not say, "Interesting, let's explore that." They say, "Something is broken here. Let's figure out what." This is not about fear. It is not about trying to avoid an uncomfortable conclusion. It is about quality control. It is about making sure that the theories we build are not just mathematically consistent, but epistemically viable. That they allow us to trust the process by which we arrived at them. And Boltzmann brain-dominated theories do not pass that test. They fail it spectacularly, because they predict that the very act of reasoning about them is probably unreliable. So what do? We look for ways out. We look for cosmological models where evolved observers, real ones, with real histories, dominate the count. Where beings like us are typical, not extraordinarily rare. Where the evidence we use to understand the universe is genuine, not a flickering accident. This pushes cosmologists in certain directions. It pushes them away from overly simple equilibrium pictures. Away from cosmologies where the universe just expands forever in a featureless de Sitter state. Away from models where the far future is dominated by rare, random fluctuations, and toward models where something changes, where the cosmological constant decays, where equilibrium is unstable, where the universe does not linger forever in a state that allows Boltzmann brains to thrive. Or, alternatively, it pushes them to rethink the way we count observers, to reconsider what typical means, to find a way of doing the accounting that does not drown real observers in an infinite sea of fake ones. These are not easy problems. They touch the deepest questions in cosmology. Questions about time, infinity, probability, and what it means to be an observer at all. But they are questions worth asking. Because the alternative, accepting a cosmology that says we are probably hallucinating, is not an option. Not because it is scary, but because it is incoherent. It asks us to believe something, while simultaneously giving us reasons not to trust belief itself. And that does not work. So when physicists talk about the Boltzmann brain problem, they are not trying to prove that Boltzmann brains exist. They are not claiming we are living in a simulation, or that reality is an illusion, or any of the dramatic narratives that sometimes get attached to this idea. They are doing something simpler and more important. They are using the Boltzmann brain as a diagnostic tool, a way of testing whether a cosmological model makes sense, whether it predicts a universe where knowledge is possible. And if it does not, if it predicts that most observers are delusional, then that model is rejected. Not because we know it is false, but because we know it is unusable. And science is, above all, about building usable theories. Theories that explain. Theories that predict. theories that we can trust. Boltzmann brain-dominated theories do not meet that standard, and so we keep looking for a cosmology that makes room for real observers, for genuine history, for reliable memory, for a universe where the past we remember actually happened. Because if it did not, then nothing we know is secure. Not the stars, not the earth, not the atoms in our bodies, not the thoughts in our minds. All of it could be false, a momentary fluctuation, a convincing illusion. And while that is a fascinating philosophical possibility, it is not a foundation you can build science on. Science requires trust. Trust in observation, trust in memory, trust in the continuity of evidence. And the Boltzmann brain, by its very nature, erodes that trust. Not by choice, not by intention, but simply by being overwhelmingly more probable than the alternative. And that is why it matters. Not as a threat, but as a test, a way of asking, does this cosmology allow for knowledge? Does it predict a universe where beings like us can exist, observe, reason, and arrive at true conclusions? If the answer is yes, we keep the theory. If the answer is no, we look for something better. And in the sections to come, we are going to explore one of the most troubling possibilities that emerges from this problem. The possibility that the past itself, the history we remember, the evidence we rely on, might not be as secure as we think. That memory, however vivid, however detailed, might not be a reliable guide to what actually happened. Because in a universe where fluctuations can create minds with false memories, how do you know your memories are not false? How do you know the past is real? This is not a question designed to frighten you. It is a question that emerges naturally from the mathematics. And it is a question we need to answer. Slowly, carefully, without rushing, because the stability of everything we believe depends on it. Because memory, too, is made of matter. Memory is not a guarantee of history. It is a shape that exists now. Close your eyes and remember something. Anything. Your first day of school. A conversation you had last week. The face of someone you love. That memory feels real. It feels like a window into the past. A record of something that happened. But what is it physically? It is a pattern. A configuration of neurons. A structure in your brain. Synapses connected in a particular way. Chemicals distributed in a particular arrangement. Electrical signals flowing along particular paths. It exists now, in the present, not in the past. The past is gone. It does not exist anymore. All that remains is the present. And in the present, there is this pattern, this structure, this shape, and that shape encodes information. It represents something. It feels like a memory. But here is the question. Does the pattern require the past to have happened? Or can the pattern exist without the past? This is not a philosophical trick. It is a straightforward question about physics. If a brain is just a collection of atoms arranged in a particular way, and if that arrangement can encode what feels like a memory, then can that arrangement appear spontaneously, without any history behind it? The answer, according to the laws of thermodynamics, is yes. Not easily, not often, but yes, because a memory is just a structure, and structures can fluctuate into existence. Most fluctuations are small, random, meaningless, but some, vanishingly rarely, are large, complex, organized, and if a fluctuation can assemble a brain, something we have already explored, then it can also assemble a brain with memories. Memories that were never experienced. Memories of events that never occurred. Memories of a world that does not exist. Not because the fluctuation is trying to deceive, but simply because the pattern that encodes memory of X can exist without X ever happening. The memory is not the past. The memory is a present structure that points toward a past. And if the structure can exist on its own, then the past it points to does not need to be real. This is the heart of the false memory problem in Boltzmann brain scenarios. In an equilibrium universe, where order appears through rare fluctuations, producing a single brain with detailed memories is far more probable than producing an entire universe with a real history. Because the brain only needs to have the right pattern now. It does not need the stars, the planets, the billions of years of cosmic evolution that would normally produce that pattern. It just needs the pattern itself. And so, in a fluctuation-based cosmology, false memories are statistically favored over true ones. Not because truth is less beautiful, not because the universe prefers deception, but simply because false memories are cheaper, simpler, more probable. They require less structure, less entropy reduction, less of a dip away from equilibrium. And in a universe governed by probability, the cheaper option wins, by an overwhelming margin. Now, before we go further, let's be clear about what this means. This does not mean your memories are false. It does not mean the past did not happen. It means that in certain cosmological models where the far future is dominated by equilibrium fluctuations, the typical observer with memories is one whose memories do not correspond to real events. And if those models are correct, then we would have to be extraordinarily atypical, extraordinarily lucky, to be real. But there is another wrinkle here, one that philosopher of physics John Norton has explored. If Boltzmann brains are produced by random fluctuations, then there is no reason to expect those brains to have orderly, coherent, law-like memories. Most fluctuations are not neat. They are messy, chaotic, irregular. And so, if a brain fluctuates into existence, its internal structure is more likely to be jumbled than organized, more likely to contain contradictions than consistency, more likely to have what Norton calls batty memories than rational ones. Imagine a brain that flickers into existence with memories of being a medieval knight, and also an astronaut, and also a tree, all at once, contradictory, incoherent, but present. That brain would have memories. It would have experiences. It would, in some sense, be conscious. But its memories would not make sense. They would not form a coherent narrative. They would not obey the usual laws of cause and effect. They would be batty. And according to Norton's analysis, batty brains are far more probable than orderly ones, because there are vastly more ways to arrange neurons into a chaotic, contradictory pattern than into a neat, law-like one. Just as there are more ways to shuffle a deck of cards into disorder than into perfect sequence. So if Boltzmann brains are produced by fluctuations, the typical Boltzmann brain should not have memories like ours. It should have broken memories, fragmented, unstable, surreal. And that is actually a point in our favor, because our memories are not batty. They are coherent, continuous, consistent. We remember a lawful world, a world where effects follow causes, where time flows in one direction, where the past connects smoothly to the present. And that coherence is evidence, not proof, but evidence. Evidence that we are not typical Boltzmann brains, that we are not random fluctuations, that our memories correspond, at least approximately, to a real history. Because if we were Boltzmann brains, we should expect to have batty memories, and we do not. So either we are extraordinarily atypical fluctuations, ones that by chance happen to have orderly law-like memories, or we are not fluctuations at all. We are the product of real evolution, real cosmic history, real stars and planets and biology. Most cosmologists prefer the second option, not because it is comforting, but because it is simpler, more consistent with the data. But the false memory problem highlights something deeper. It shows us that memory and history are not the same thing. Memory is a present structure. History is a sequence of past events. Normally, we assume they match. We assume that if you have a memory of X, then X happened. But that assumption is not guaranteed by the laws of physics. It is only guaranteed if you are part of a world with a real, continuous history. A world that evolved from low entropy to high entropy over billions of years. In a fluctuation-based cosmology, that guarantee disappears. And what you are left with is the possibility, however remote, that memory and history come apart. That you can have the memory without the event. The pattern without the past. This is not horror. It is not meant to frighten you. It is just a consequence of taking thermodynamics seriously. Of asking, what happens when we extend these equations to their logical conclusion? And the answer is, strange things. Unintuitive things. Things that challenge our everyday assumptions about what is real and what is evidence. Because evidence, at the end of the day, is always embedded in the present. We look at fossils now. We measure starlight now. We examine our memories now. And we infer a past from those present structures. But that inference depends on an assumption that the structures were caused by the past, that they were built up over time through lawful processes. In a normal cosmology, that assumption is safe. But in a fluctuation-dominated cosmology, it is not. Because fluctuations can create structures that look like evidence without actually being caused by what they represent. A fossil that was never a living creature. Starlight that never traveled from a distant galaxy. Memories that never corresponded to real events. All of it present. All of it convincing. None of it real. This is the deep, unsettling part of the Boltzmann Brain problem. Not that experience is impossible, but that experience can be disconnected from a genuine past. That you can have all the internal markers of reality, memories, sensations, coherent impressions, without any of the external history that would normally produce them. And if that is possible, then how do you know it is not happening? How do you know you are not a Boltzmann brain right now, convinced of a history that never was? The short answer is, you do not know. Not with absolute certainty, but you have evidence. The coherence of your memories, the lawfulness of your experiences, the consistency of the world around you. All of that points toward a real history, a genuine past. And while it is not proof, it is reason enough to believe. At least, in the absence of a better alternative. But the false memory problem does not stop at individual brains. It scales, because if a fluctuation can create a single brain with false memories, then, in principle, a larger fluctuation could create multiple brains, or an entire room full of people, or a city, or a planet, all with false memories, all convinced of a history that never happened. The larger the fluctuation, the rarer it is, by an enormous margin. But it is not impossible, just less probable. And in an infinite future, less probable still happens, infinitely many times. So the question becomes, at what scale does the false history stop? If your memories are false, are your friends' memories also false? Are the books you read false? Are the stars you see false? How much of the world around you is part of the fluctuation, and how much is real? This is the question we turn to next. The possibility that not just your mind, but the entire observable universe could be a temporary fluctuation, a bubble of order in an endless sea of equilibrium, real for a moment, and then gone. This is not a claim. It is a possibility that emerges from the mathematics, a strange, patient consequence of taking probability seriously. And it is where the Boltzmann brain problem expands into something larger, something that challenges not just our memories, but our entire sense of what is real. We will explore that carefully, without fear, without rushing, because the question is worth asking, even if the answer is uncertain, even if it flickers. And once a brain can form, so can the world around it. Reality can be convincing, even when it is brief. We have been talking about Boltzmann brains as isolated minds, disembodied, floating in the void, flickering into existence for a moment, and then dissolving back into equilibrium. But there is no reason to stop there, because if a fluctuation can assemble a brain, it can also assemble more. A brain inside a skull attached to a body sitting in a chair in a room in a building on a street, and so on. The larger the structure, the rarer the fluctuation, the more improbable it becomes. But it is not impossible, just less likely, and in an infinite future, less likely still happens. This is what Sean Carroll has pointed out in his work on the Boltzmann brain problem. The issue is not just minimal minds. It is a spectrum. At one end, you have the simplest possible observer, a bare brain, just enough neural structure to support a moment of awareness. No body, no environment, no context. At the other end, you have something much larger, a brain in a body in a world, a fully realized environment that looks, feels, and behaves exactly like the reality you experience now, complete with stars, planets, history, memory, all of it a fluctuation, all of it temporary, all of it false. This is the architecture of a false reality, and it emerges naturally from the same logic that produces Boltzmann brains, because there is no sharp line between brain and world. They are both just patterns, both configurations of matter and energy, both structures that can, in principle, fluctuate into existence. The difference is only one of scale, of size, of how much order you need. And while larger fluctuations are exponentially rarer than smaller ones, they are not ruled out. They are just further along the spectrum. So let's walk through this carefully. Imagine a fluctuation that produces a brain. Just the brain, floating in space, conscious for a moment, then gone. That is the minimal Boltzmann brain, the simplest case. Now imagine a slightly larger fluctuation, one that produces not just a brain, but also a skull, skin, eyes, a body. This body has no history. It was not born. It did not grow. It simply appeared, fully formed in the void. But internally, it is indistinguishable from a real body. It has the right anatomy, the right chemistry, the right neural patterns, and the brain inside it has memories. Memories of growing up, memories of living, memories of a world. None of those memories are real, but the brain does not know that. From its perspective, everything is normal. Now imagine an even larger fluctuation, one that produces not just a body, but also a room around it. Walls, furniture, windows, light coming through the windows. The body is sitting in a chair. The brain is awake, aware, looking around, and everything it sees is consistent, coherent, lawful. The room looks like a room. The light behaves like light. The objects have weight, texture, solidity. From the inside, there is no way to tell that this is a fluctuation, that none of it has a history, that it all appeared fully formed just a moment ago. Because fluctuations do not care about consistency. They can produce any configuration, including configurations that look exactly like the result of billions of years of cosmic evolution. They just have to get the pattern right. And if the pattern is right, then the experience is indistinguishable from reality. Now imagine an even larger fluctuation, one that produces not just a room, but an entire building, a street outside, other buildings, other people, a whole neighborhood, a city, a planet, all of it appearing at once, fully formed, complete with fake histories encoded in every brain, every book, every fossil, every star. This is a maximal false reality, a universe that looks, from the inside, exactly like ours. But that has no past, no history, no long causal chain leading back to a Big Bang. Just a single, impossibly rare fluctuation, lasting for a moment, and then dissolving. This sounds absurd, and in a sense it is, because the probability of such a fluctuation is unimaginably small. Far, far smaller than the probability of a single Boltzmann brain. But here is the key point. It is not zero, and in an infinite future, non-zero probability means it will happen. Eventually, somewhere, infinitely many times. So now we face a troubling question. If we are trying to figure out whether we are typical observers, and if the universe allows for fluctuations at every scale, then what are we? Are we minimal Boltzmann brains? Isolated minds with false memories? Or are we slightly larger fluctuations? Brains in bodies? Or even larger? Brains in bodies in rooms? Or are we part of a maximal fluctuation? An entire fake universe, complete with stars and galaxies and history? Or are we real? The product of genuine cosmic evolution. A low-entropy Big Bang. Billions of years of structure formation. Stars. Planets. Biology. The math does not tell us. It only tells us that, in a fluctuation-dominated cosmology, the fluctuation-based observers vastly outnumber the real ones. By every measure. At every scale. And so, if you are a typical observer, you should expect to be a fluctuation. Not necessarily a minimal one, but a fluctuation nonetheless. And that is the problem. Because if most observers, even the ones who seem normal, who have coherent memories, who live in worlds that appear lawful, are actually fluctuations, then there is no secure link between what you experience and what is true. Your evidence, however convincing, could be false. Your memories, however vivid, could be fabricated. Your world, however solid, could be temporary. And there would be no way to know. This is what Carroll means when he emphasizes that the Boltzmann brain problem is not just about weird, minimal observers. It is about observers who are locally identical to us, who have all the same experiences, all the same memories, all the same sense of living in a real, continuous world, but who, nonetheless, arise from fluctuations rather than evolution. Because once fluctuations can mimic reality perfectly, the distinction between real and fake collapses, at least from the inside. And if fluctuations dominate the count of observers, then most apparently normal observers are fluctuations, and you statistically should expect to be one of them. This is the deep, unsettling conclusion that emerges from taking the Boltzmann brain problem seriously. Not that your experience is impossible, but that your experience could be entirely disconnected from the cosmological history you believe in. That everything you see, everything you remember, everything you take as evidence of a real past, could be part of a temporary bubble, a fleeting fluctuation, a convincing illusion. Not an illusion in the sense of being unreal to you, but an illusion in the sense of not having the history it appears to have. Because reality, at the end of the day, is a pattern, a structure, a configuration. And if that configuration can exist without the history, then the history is not guaranteed by the experience. You can have all the internal markers of a real world, continuity, coherence, lawfulness, without any of the external history that would normally produce them. And that is what makes the false reality problem so difficult to escape. Because the question is not, is my experience real? The experience is real. You are having it. Right now. The question is, does my experience have the history I think it does? And in a fluctuation-dominated cosmology, the answer is, probably not. Now, before this becomes too heavy, let's step back. Because this is not a claim about what is true. It is a claim about what certain cosmological models predict. And as we have discussed, those models are probably wrong. Or at least incomplete. Because a model that predicts you are probably a fluctuation is a model that undermines its own justification. It says, trust this theory. But also, your evidence for this theory is probably false. And your reasoning about this theory is probably unreliable. And your memory of learning this theory is probably fabricated. That does not work. A theory that predicts you should not trust it is not a theory you can use. And so, most cosmologists treat the Boltzmann Brain problem and its extension into false realities as a diagnostic, a way of testing whether a model is viable. If a model predicts that most observers are fluctuations, even observers who seem normal and coherent, then that model fails the test. Not because fluctuations are impossible, but because a model that predicts you are probably a fluctuation cannot be justified by the evidence you have. Because that evidence is part of the fluctuation, and so the model collapses under its own weight. This is cognitive instability again, but now applied not just to brains, but to entire worlds. If the world you see is probably a fluctuation, then the cosmology you believe in, which predicts that fluctuation, is also probably part of the fluctuation, which means it is probably false, which means you should not believe it. And around it goes. A loop, a paradox, a breakdown. And that breakdown tells us something important. It tells us that we need a different kind of cosmology, one that does not predict fluctuation-dominated futures, one that preserves the link between observation and reality, one that allows us to trust our memories, our evidence, our sense that the past is real. Because without that trust, science itself becomes impossible. Not because the universe is trying to deceive us, but because a cosmology that predicts deception cannot be confirmed by the very beings it claims are deceived. So where does that leave us? It leaves us with a choice. Either we find a way out of the fluctuation-dominated future, a mechanism that prevents the universe from lingering forever in equilibrium, a decay of the cosmological constant, an instability in de Sitter space, or we rethink the way we count observers, find a measure that privileges real, evolved observers over fluctuation-based ones, a way of weighting the probabilities that does not drown us in false realities, or we accept that there is something deeper we are missing, some principle, some structure, some aspect of quantum mechanics or gravity or consciousness that changes the picture entirely. These are open questions, hard ones, deep ones, but they are questions worth asking, because the alternative, accepting a cosmology where most observers are fluctuations, where most realities are false, where most experiences are disconnected from genuine history, is not viable. Not because it is frightening, but because it is incoherent. It asks us to believe something, while simultaneously giving us reasons not to trust belief itself. And that is not a foundation you can build knowledge on. So we keep looking for a cosmology that makes sense, that predicts a universe where beings like us are natural, not miraculous, where the past we remember actually happened, where the evidence we rely on is genuine. And as we search, we hold on to this. The coherence of your experience is evidence. Not proof, but evidence. Evidence that you are not a minimal fluctuation, not a brain in a void, not a temporary illusion, but a real observer, in a real world. with a real history, a history that stretches back billions of years, to stars, to galaxies, to a Big Bang, a history that is long, complex, and lawful. And while we cannot prove that history with absolute certainty, while the possibility of fluctuation can never be entirely ruled out, we can say this: the simplest explanation for your coherent, continuous, law-like experience is that it is real, that the past happened, that the world exists, that the stars are distant, not false, and that you are not flickering. You are here, and that is enough. For now, and this is where we soften, stability leaves fingerprints, and our world is full of them. We have walked through the mathematics. We have explored the paradox. We have looked at the strange consequences that emerge when you take probability and thermodynamics seriously in an infinite future. And now we turn back, not to certainty, not to proof, but to something quieter, to the evidence of coherence, to the fingerprints of continuity, to the reasons, good reasons, to believe that we are not Boltzmann brains. Let's start with what we know. The Boltzmann brain is not a mainstream claim. It is not a prediction that cosmologists take seriously as a description of you, or me, or anyone living in the present universe. It is a diagnostic, a tool, a way of testing cosmological models at their extremes. When physicists talk about Boltzmann brains, they are not saying, you might be one. They are saying, if this theory predicts you are probably one, then this theory is broken. And that is an important distinction, because the goal is not to prove Boltzmann brains exist. The goal is to avoid cosmologies where they dominate, to find models of the universe where evolved observers, real ones like us, are typical, where the past is genuine, where memory is reliable. And most of the cosmological work being done today is aimed at exactly that, at finding ways out of the Boltzmann brain problem, ways to preserve the link between observation and reality. So if you have been feeling unsettled by the possibility that you might be a fluctuation, a temporary illusion, a brain flickering in the void, you can let that go, not because it is impossible, but because it is extraordinarily unlikely. And here is why. First, your experience is stable. You do not flicker. You do not dissolve. You persist. Hour after hour, day after day, year after year. Your memories connect. Your experiences flow continuously. The world around you behaves in predictable, law-like ways. And that stability is evidence. Because in a Boltzmann brain scenario, stability is not what you would expect. Remember what John Norton argued. If Boltzmann brains are produced by random fluctuations, then the typical Boltzmann brain should have batty memories. Chaotic, contradictory, incoherent, because there are vastly more ways to assemble neurons into a jumbled pattern than into an orderly one. And so, if you were a Boltzmann brain, you should expect to have broken memories, fragmented impressions, a sense of confusion, timelines that do not connect, experiences that contradict each other. But you do not have that. Your memories are coherent. They form a continuous narrative. They obey the laws of cause and effect. They connect to each other in sensible ways. And that coherence is a fingerprint of stability, of a real history, of genuine continuity. Not proof, but evidence. Strong evidence. Second, your experience is cross-checkable. You do not just have memories. You have records, books, photographs, other people who remember the same events you do. You can verify your past. You can compare notes. You can test whether your recollection matches external evidence. And when you do that, you find consistency, agreement, overlap. That is not what you would expect in a fluctuation-dominated cosmology. Because in that picture, each observer is isolated. Each one is a separate fluctuation. There is no reason for their memories to align. No reason for their experiences to match. But ours do. We share a world. We share a history. We corroborate each other's experiences. And that shared coherence is another fingerprint. Another piece of evidence that we are not isolated fluctuations, but participants in a genuine, continuous reality. Third, the world around you is law-like. Physics works. Chemistry works. Biology works. The same rules apply today as they did yesterday, as they will tomorrow. Objects fall. Light travels. Water freezes. Stars burn. All of it predictable. All of it consistent. All of it following patterns that we can measure, test, and understand. And that lawfulness is exactly what you would expect if the universe has a real history. If it evolved from a low-entropy initial state through billions of years of structure formation. It is not what you would expect if the universe is a temporary fluctuation, because fluctuations are not constrained by history. They can produce any configuration, including configurations where the laws of physics are different, or inconsistent, or chaotic, but we do not see that. We see order, regularity, predictability, and that order is evidence. Evidence that the world is not a brief illusion, but a long, genuine unfolding. Now, let's return to the cognitive instability argument. Sean Carroll has pointed out that Boltzmann brain-dominated cosmologies are self-undermining. If a theory predicts that most observers are Boltzmann brains, and therefore that their evidence is probably false, then you cannot rationally trust the reasoning that led you to accept that theory, because that reasoning is part of the evidence, and the theory says the evidence is unreliable. So you end up in a loop, a paradox, a breakdown, and that breakdown is not a feature. It is a bug. It tells us that the theory is flawed, that something in the model is wrong, that the cosmology needs to be revised. And so, rather than accepting Boltzmann brain dominance as a lived reality, cosmologists treat it as a warning sign, a signal that the model has failed a basic self-consistency test, and they look for alternatives, for cosmologies that do not predict Boltzmann brain dominance, that preserve the link between observation and reality. Many such alternatives are being explored. Some focus on limiting the duration of late-time equilibrium, on finding mechanisms that prevent the universe from staying in a de Sitter-like state forever. Others focus on vacuum decay, the idea that the vacuum states we think are stable might actually be metastable, that they might decay on some timescale, transitioning into lower energy configurations. If that happens, then the infinite future is cut off, or at least changed, and Boltzmann brains, which rely on infinite time to become numerous, might not dominate after all. Don Page, among others, has analyzed this in detail. He has looked at the timescales for vacuum decay and how they relate to the Boltzmann brain problem. And what he has found is that if vacua decay quickly enough, on timescales that are still extraordinarily long by human standards, but finite, then Boltzmann brains can be avoided. The universe does not linger forever in a state where fluctuations dominate. It transitions, it changes, it moves on, and in that picture, evolved observers remain typical. Real history remains the norm. Other approaches focus on the measure problem, on finding better ways to count observers in infinite or very large universes. Ways that do not simply count every observer equally, regardless of when or how they appear, but that weight observers according to some principle, perhaps related to causation or entropy or the structure of space-time itself. That privileges real, evolved observers over fluctuation-based ones. These are technical challenges, deep ones, not yet fully solved, but the fact that people are working on them is itself a kind of reassurance, because it means that the cosmological community has not accepted Boltzmann brain dominance as an inevitability. They have treated it as a problem, a puzzle, something to be solved, and they are actively looking for solutions. So where does that leave us, practically speaking? It leaves us with calm, not certainty, not absolute proof, but calm, because the evidence, the coherence of your experience, the stability of your memories, the lawfulness of the world, the cross-checkability of your observations, all points in the same direction, toward a real history, a genuine past, a universe that evolved from a low-entropy Big Bang through billions of years of structure formation, towards stars and galaxies and planets and biology, toward you, here, now, not as a fluctuation, but as the product of all that history. And while we cannot rule out the possibility of fluctuations with absolute certainty, while the mathematics will always allow for them, however rare, we can say this: the simplest explanation for your experience is that it is real, that the past happened, that the world exists, that you are not flickering, and that simplicity is not laziness. It is reason. It is Occam's razor. It is the principle that, when faced with multiple explanations, we favor the one that requires the fewest assumptions. A real history requires no miracles, no extraordinary luck, no statistical anomalies. It is just what happens when a low-entropy universe expands and cools and forms structure over billions of years. A Boltzmann brain, on the other hand, requires an extraordinarily rare fluctuation, a statistical accident so unlikely that it should almost never happen. And while almost never is not the same as never, it is close enough. Close enough to say, you are probably real. Your memories are probably genuine. Your world is probably continuous. Your past probably happened, not with absolute certainty, but with enough confidence to trust, to believe, to move forward. And that is the practical takeaway. Boltzmann brains are a tool for sharpening theories at extreme timescales, for testing whether cosmological models make sense when you push them to their limits. They are not a prediction about your ordinary life, not a claim about your present experience, not a reason to doubt the ground beneath your feet. They are a thought experiment, a mathematical consequence, a way of asking, does this theory predict a universe where knowledge is possible? And if the answer is no, we reject the theory, not the knowledge. So as we move toward the close of this journey, let's hold on to this. You are here. You are real. You have a history, a long history, billions of years of cosmic evolution, stars forming, planets cooling, life emerging, consciousness awakening, all of it leading to this moment. And while the mathematics will always allow for the possibility that it is all a fluctuation, that the past is false, that the world is brief, the evidence does not support that. The evidence supports continuity, reality, genuine unfolding, and that is enough, not to erase uncertainty, but to live with it, to move forward, to trust, as much as we reasonably can, that the world is what it seems. Because in the end, that is all we ever have. Not proof, but evidence, coherence, stability, the quiet fingerprints of a real, continuous world. And if those fingerprints are convincing, then we are justified in believing them. Not because we can rule out every alternative, but because the alternative, that we are isolated fluctuations, briefly convinced of a false reality, is so much less probable, so much less supported by what we see, what we remember, what we experience. And so we choose reality, not blindly, but reasonably, with open eyes, with full awareness of the possibilities, with humility about what we can know, but also with confidence, quiet confidence, in the coherence of our experience, in the continuity of our world, in the fact that we are here, now, not flickering, but persisting, and that persistence is real. And now, we let the thought rest. Not every question needs an answer. Some are meant to be lived with quietly. We have traveled a long way tonight, through probability and entropy, through fluctuations and false memories, through paradoxes that turn inward and theories that question themselves. And now, we arrive at something simpler. Not an answer, not a conclusion, but a place to rest. Because the Boltzmann brain is not ultimately about brains. It is about something deeper. It is about what it means to exist in a universe governed by physics. A universe where meaning is not guaranteed, where narrative is not inevitable, where the story you believe you are living is not written into the fabric of reality itself. It is about recognizing that the coherence you experience, the continuity of memory, the stability of the world, the lawfulness of cause and effect, is not a given. It is a gift, a rare gift, a temporary gift, a gift that arises only in certain eras, in certain conditions, far from equilibrium, in universes that have structure, history, time flowing in one direction. In most of cosmic time, if the far future is what we think it might be, that gift disappears. The universe becomes flat, featureless, silent, and in that silence, there is no narrative, no continuity, no observers with long histories and coherent memories, only flickering, rare, brief. But here, now, in this era, narrative exists. You exist, and that existence is not just a physical fact. It is a meaningful one, because meaning requires continuity. It requires connection. It requires that one moment leads to the next in a way that can be remembered, understood, traced. And the Boltzmann brain problem shows us that continuity is not automatic. It shows us that evidence and memory are not guarantees of history. They are physical structures, patterns, shapes in neurons and molecules and fields. And those shapes can, in principle, exist without the history they point to. A memory can be real, physically present, neurologically active, without the event it remembers ever happening. A piece of evidence can exist, a fossil, a photograph, a star, without the long causal chain that would normally produce it. In principle, not in practice, not here, not now, but in principle, and recognizing that possibility changes something. It makes you aware that knowing depends on something fragile, something that can break. It depends on reliable connections between moments, on the assumption that the past you infer from present structures is genuine, that the chain of cause and effect is unbroken. And in a normal cosmology, one where the universe evolves from a low entropy beginning through billions of years of structure formation, that assumption is safe. The connections are real. The history is genuine. The narrative is continuous. But in a fluctuation-dominated cosmology, that assumption breaks down, and with it, the ability to know anything at all. This is why the Boltzmann Brain problem is not just a physics problem. It is a philosophical one. It forces cosmology to ask questions that science usually avoids. Questions about typicality, about inference, about what counts as an observer, about how we define probability in infinite spaces. These are not small questions. They touch the foundations of knowledge itself, because science is built on observation, on evidence, on the assumption that what you see reflects, at least approximately, what is real. But if most observers are hallucinations, then that assumption fails, and science collapses, not because the universe is hostile, not because reality is trying to deceive, but because the theory itself predicts that the process by which you arrive at the theory is unreliable. And that is a breakdown, a fundamental one. A theory that undermines its own justification cannot be used, cannot be trusted, cannot stand. It is mathematically consistent, logically coherent, but epistemically unusable. And that unusability is what makes the Boltzmann brain so important. It is not a claim about what is true. It is a test, a filter, a way of asking, does this cosmology allow for knowledge? Does it predict a universe where observers can trust their evidence most of the time? If yes, the theory passes. If no, it fails. And we keep looking for a cosmology that makes room for real observers, for genuine history, for continuity, for a universe where knowing is possible. And that search is still ongoing. The measure problem has not been solved. The question of how to count observers in infinite or very large universes is still open. The fate of the cosmological constant, whether it lasts forever or decays or is replaced by something else, is still uncertain. The ultimate structure of space-time, the nature of quantum gravity, the deep principles that govern the far future, all of these are unresolved. And they may remain unresolved for a long time. But that is okay, because the point is not to have all the answers. The point is to ask the right questions. And the Boltzmann brain has given us one of the deepest questions we can ask. What does it mean to be real? Not metaphysically, not abstractly, but concretely, physically, in a universe governed by probability and entropy. What does it mean to have a history that is genuine, not fabricated? A memory that is reliable, not false? A world that is continuous, not flickering? And how do we build a cosmology that preserves those things? That allows us to trust what we see, to believe what we remember, to know that the past we infer from present evidence actually happened. These are the questions we are left with, and they do not have easy answers, but they have good answers, partial answers, answers that are being refined, tested, explored, answers that say, you are probably real, your history is probably genuine, the world is probably continuous, not with certainty, but with enough confidence to live, to trust, to move forward. And that is what we do. We live with uncertainty. We hold questions without answers. We accept that some things cannot be proven, only believed. But we believe reasonably, with evidence, with coherence, with the quiet fingerprints of stability all around us. And those fingerprints are enough. Enough to say, the world is real. The past happened. The stars are distant, not false. Enough to trust the ground beneath your feet, the thoughts in your mind, the continuity of your experience. Not because you have ruled out every alternative, but because the alternative is so much less likely, so much less supported, so much harder to reconcile with what you see. And so you choose reality, not blindly, but with open eyes, knowing that the mathematics allows for strange possibilities. knowing that the edges of cosmology are uncertain, knowing that the far future might be different than we imagine, but knowing also that here, now, in this moment, coherence holds, continuity holds, and that is enough. The Boltzmann brain is not a monster. It is not a threat. It is not a claim about your life. It is a reminder that meaning is not guaranteed, that narrative is fragile, that the universe does not owe us coherence, but it has given it to us. Here, now, in this era, and that is a gift we can appreciate, a gift we can trust, a gift we can live within. Not forever, perhaps, but for now, and now is all we have. Not the past. The past is gone. It exists only as structure in the present, as memory, as evidence, as patterns that point backward. Not the future. The future has not arrived. It exists only as possibility, as prediction, as hope. Only now, this moment, this breath, this quiet awareness. And in this moment, you are here. Not flickering, not dissolving, not about to vanish into equilibrium. Here, real, continuous, connected to a history that stretches back billions of years, and forward into whatever comes next. That continuity is not something you have to prove. It is something you experience, directly, immediately. Every moment flows into the next. Every thought connects to the one before. Every sensation arises and fades in a continuous stream. And that stream is real, not because you can prove it philosophically, not because the mathematics demands it, but because it is what you live, and living it is enough. So let the questions rest. Let the paradoxes linger. Let the uncertainties remain. You do not have to resolve them tonight. You do not have to know with certainty whether the cosmological constant will last forever, or whether the measure problem has a solution, or whether the universe will one day be dominated by fluctuations. Those are questions for cosmology, for mathematics, for future generations of physicists and philosophers. For you, tonight, the question is simpler. Are you here? And the answer is yes. You are here. You are real. You have a history. And that history continues, moment by moment, breath by breath, not because it is guaranteed, but because it is happening, right now. And that is enough. The universe may be strange at the edges. The far future may be uncertain. The mathematics may allow for things we cannot fully imagine. But here, tonight, in this moment, you are stable. You are continuous. You are real. And that reality is not diminished by the existence of strange possibilities in distant futures or infinite timescales. It is not weakened by the knowledge that memory is a physical pattern, or that evidence is a structure in the present, or that narrative is a rare gift. If anything, it is strengthened, because now you know what you have. Now you know how rare it is, how fragile, how temporary, and how precious. The coherence of your experience, the continuity of your world, the lawfulness of cause and effect. These are not things to take for granted. They are things to appreciate, to live within, to honor, not with fear, not with anxiety, but with quiet gratitude, for the gift of existing in an era where meaning is possible, where narrative unfolds, where knowing is real. And so we rest here, not with answers, but with presence, not with certainty, but with trust, not with proof, but with coherence. And that coherence is enough. It has always been enough. It will continue to be enough, for as long as you are here, and you are here, now, real, continuous, not flickering, not fading, here, and that is everything. The Boltzmann brain taught us to question, to doubt, to look at the edges of what is possible, but it also taught us to appreciate, to trust, to recognize what we have, and what we have is this: a moment, a breath, a world, continuous, coherent, real. And in that world, you exist. Not as a fluctuation, not as an accident, not as a brief, convincing illusion, but as a product of history, of billions of years, of stars and planets and evolution, of a universe that, for now, supports narrative. And that is enough. More than enough. It is everything. So rest now. Let the questions remain. Let the uncertainties linger. You do not have to solve them. You do not have to know. You only have to be. Here. Now. Real. And you are here, and the night continues, quietly, continuously, without end. Closing paragraph. And now, there is nothing left to think about. The questions can stay where they are. The universe can remain vast, uncertain, and unfinished. You do not need to resolve it tonight. You are allowed to rest inside the coherence of this moment, inside the quiet fact of being here. Breath follows breath. Thought fades into silence. And whatever the universe becomes, whatever the far future holds, none of it is required right now. For now, there is only rest. And that is enough. So let the questions rest where they are. They do not need answers tonight. The universe can remain vast, unfinished, and quietly unresolved. You are allowed to stop reaching outward now. Allowed to rest inside the simple fact of being here. Breath following breath. Thoughts softening into silence. Whatever the cosmos becomes, whatever the far future holds, none of it is required of you in this moment. For now, there is only this calm continuity, this quiet presence, this real, unbroken now. Sleep gently. The night is patient, and everything that matters can wait. Good night.